Thanks everyone for joining us today. I appreciate you guys being here. I know this is the last webinar of the year for us, and I hope everybody has a happy holiday and great end of the year. We will go ahead and get started. All right, so as always, just a little bit of housekeeping. Today we have a webinar today, the benefits of, actually we've renamed it. So it's IECC Energy Code requirements for demand controlled hot water recirculation. We've got Juliana, and Juliana, is Gabe going to be on?
I'm right here.
Oh, there you go. And
Yep,
Gabe's
thank
on
you.
today. So I'll get you guys introduced here shortly. Just let me run through this first one. As always, the webinar is being recorded today. It will be uploaded to our YouTube channel where you can find it by searching SPEAR on YouTube, or you can go directly to our website at eepartnership.org. And then under our news section, you'll find our resources page. If you go to our YouTube channel, we've got over 150 videos in climbing from just different varieties of training topics and local government topics. Today's webinar is, as always, eligible for ICC CEUs. You must be present for at least 3/4 of the presentation. Within about 72 hours after this is adjourned, you'll receive a course evaluation email from Kathy Lawrence. Please be sure and fill that survey out, add any notes that you want in there, give us some ideas of next year webinar topics that you want to talk about and discuss and go into more depth into, even though we've covered it. If we've covered it last year, we can cover it again next year in more greater detail. She'll send you that after the survey's return. You'll get a certificate that contains the title and the course number that you'll need when you're reporting your CEUs to ICC. As always, I have the chat feature open. Report any technical difficulties or questions you might have during that, and also the Q&A is open. You guys can post questions in there as well. Again, today we've got Gabe and Juliana. Juliana's from Innovative, and Gabe is from Auto Hot USA. They're going to talk to us about some recirculation. It's the code requirement. If you're going to use it, there's a requirement for that. If you're new to our channel or new to our YouTubes, we're SPEAR. We're a nonprofit. We're one of 6 RIOs. It's a regional energy efficiency organization that covers the U.S. SPEAR covers Texas and Oklahoma. We are member-based, nonprofit 501c3. So we have a wide variety of members across the energy efficiency industry, from manufacturers, from third parties, from cities, and other people that are interested in pushing forward the energy efficiency for Texas and Oklahoma. So I can always help with training. If you guys want to reach out to me, I'm trying to book my schedule for next year. I am free to do in-person trainings for Energy Code training, also ASHRAE 90.1 as well. So with that, I will turn over the controls. Let me stop sharing and you guys can take over.
All right, cool. So off we go. So today we're going to talk about a topic that's very near and dear to me. It's all about hot water distribution. So it has nothing to do with how we're heating water. It's how we're distributing that hot water once it's heated to the point of use, and doing so in a manner that's both water and energy efficient. So, and we're going to address specifically the code language in IECC for residential construction. So a little bit about who Innovative Manufacturing is. We're based in California. We manufacture control systems for residential, multifamily, or commercial buildings with an ear towards meeting energy code compliance. So I like to start off with this and just kind of set the stage. How big is hot water? I think, when we talk about, home energy use, I think hot water sometimes gets often overlooked. But as we can see in the data, is that it is roughly the first or second largest energy consumer of a house. And an average house uses about 50 to 60 gallons of hot water per day. And about roughly 20 to 23% of the water is wasted during the draw to get hot water. So hot water is a big issue for home energy use. And I also want to point out that there is a connection, there's a nexus or a relationship between water and energy. There is embedded energy in the water that we consume, even before we heat it. You think about the energy that it takes to treat the water, to transport the water. We're talking about very large, pumping systems. In California, where I live, The water that comes out of my faucet comes from several hundred miles north of us, and it has to get pumped over two mountain ranges to get to Los Angeles. So there's an incredible amount of embedded energy. So anytime we're wasting water, we're simultaneously wasting energy. And then also, water systems in the US consume approximately 3% of the total annual electricity, which is kind of an interesting thought, right? I mean, so this just sort of, further supports how inextricably linked the water and energy nexus is. So they estimate that approximately 2 gallons of water are consumed per kilowatt hours of electricity produced.
That Chris,
So now let's
I
talk.
mean, Gabe,
Yeah.
sorry, Gabe, just break in. That answers the question as to why water's making it into the energy code, is we
Mm-hmm.
see the energy consumption from that. A lot of people say, what does that have to do with energy? Thanks for answering that.
Yeah, absolutely. Yeah. So water and energy are linked. And so we have to, yeah, so we have to solve the problem of, when we talk about building efficiency, it's not just energy, it's also water efficiency as well. So now let's talk about hot water distribution. What is hot water distribution? So we have different types of architectures and topographies of hot water plumbing in our buildings. We have, what we would call, we could divide them up into two categories: residential and commercial, right? So residential would be single family homes, or a multi-unit, multi-family building where each unit has its own individual water heater. And then we have what we call commercial, where you have much larger systems. And this would be like multifamily buildings that have central water heating, or hospitals or dorms, those types of buildings. But, we often, kind of interchange residential and commercial. And sometimes there's sort of like an overlap between these two, because you might have a commercial building, but the actual hot water system might resemble more of like what you'd find in a residential home. So like, maybe a small office building, for example, or like a small, box retail store. Maybe they just have a few fixtures with a 60-gallon water heater. Well, yes, technically it's going into a commercial building, but is it really commercial water heating? So there's this little bit of an overlap here. So for the purpose of today's conversation, we're just going to be focusing on the residential. We're not going to go into large commercial because it's a whole nother beast altogether. So we want to try to keep it simple. Can a hot water system in a commercial building resemble a residential type system, and vice versa? The answer is yes. We've seen, some homes, I'm sure there in Texas too. You got some huge homes that have, 5 to 10 ton, package units, and, stuff that you would not ordinarily see in a typical residential home. And then, like the example I was saying before, smaller, light commercial buildings that have fewer fixtures. Okay, so now here's the question that I think we can all somewhat relate to. Why are we waiting for hot water? And every answer is going to be different, right? All of our homes, we wake up in the morning, we turn on a shower, we turn on a faucet, and there's going to be some wait time for hot water. Sometimes it's very quick. Sometimes it's like, 15 seconds. Other times it could be 5 minutes. And so here's the answer as to why we're waiting for hot water, particularly in new construction. Over the years, the median US home has gone from about 1,600 square feet on average to about 2,500 square feet. And so the average distance from the water heater to the farthest fixture has more than doubled. The number of fixtures have doubled. Pipe diameter has increased by a magnitude of 2 to 3 times. And fixture flow rate has been reduced by a magnitude of 2 to 3 times. So you take all of these things in consideration, right? In new construction now, it takes almost 20 times as long to get hot water versus homes that were built, 40, 50 years ago. I mean, we all remember the old shower heads that were like a fire hose. When I first moved to California 20 years ago, the standard was 2.5 gallon per minute flow at the shower head. Well, now plumbing code in California is 1.5 GPM. The bathroom aerators are going down as low as 0.5 GPM. So, some of these things that have been put into plumbing code in order to conserve water have the unintended consequence of taking much longer to get that hot water to the fixture. So, what types of hot water distribution configurations are there? The most basic kind is what we call standard trunk and branch, or just standard plumbing. And this is what we would see in most homes where you have the water heater on one side, and all of the fixtures are plumbed in series, where until the main trunk line sort of deadheads at the end of the house. And off of that main trunk line, you have the branches that feed each individual fixture. The pros are that it's the most basic and easy plumbing layout. But the cons is that it can take a very long time to get hot water. And so you waste a lot of water, you have larger diameter pipe and more heat losses. Another type, what we're seeing in energy codes, which is becoming sort of the gold standard, is what they refer to as a compact plumbing design. In some states, you get an energy credit for building a home with a compact plumbing design. Now, what does that mean? It means that the water heater is more centrally located in the house, and that the plumbing runs to each fixture is not going to be more than about 20 feet or so of half-inch or three-quarter plumbing. Now, the house that I grew up in Minnesota, we had the water heater in the basement right in the middle of the house, and the pipe came up and it fed the kitchen and the bathroom, and we never had to wait more than about 10 to 15 seconds for hot water. And that truly, that was a 1940s home. That was a truly compact plumbing design. In other states where, you don't have basement foundations like, slab on grade here in the Southwest, typically the builder's putting the water heater in the garage, right? Because that's where, if that tank ever starts to leak, it's just going to run off into the street, right? So that's the most practical place to put the water heater. So compact plumbing designs, although they do offer the most efficiency in terms of water, and you have less shorter plumbing runs, so there's less heat losses as well. But the cons is that it is less practical to implement. So we see that a lot of builders are not able to achieve this. There's the home run manifold. I think this might be a little more common in the Texas market. And we've seen this sort of kind of pop up in different parts of the country. The pros is that you have basically this manifold, and you can isolate each individual fixture in the house, and you can get consistent pressure to each fixture. You have the ability, if you need to change out a fixture, you don't have to shut off water for the whole house. You can just valve off that one fixture and replace a cartridge or whatever you need to do. The cons of a home run manifold is that it uses approximately 2.5 times as much pipe as other distribution methods. So it's more expensive, more costly to do these home runs. And there's much more standing water in the pipe. So what does that mean? If you have more standing water in the pipe, it means that you have more heat losses. Your water heater has to cycle on more frequently. So there's more of an energy cost to it. And it still doesn't resolve the issue of having to wait a long time for hot water in the waterways. Last but not least, we have hot water recirculation systems. And these types of systems are becoming more and more prevalent, more popular with builders and with new home buyers. The pros is that you get fast hot water, right? You can minimize the wait time for hot water and save thousands of gallons of water per year. But if it's not done properly, these can be the most energy costly systems to operate. So now let's turn our focus to the hot water distribution of hot water recirculation. As I said, this is becoming a more and more popular item for builders to offer their homeowners. And the reason is because it decreases the hot water time to tap. It provides the convenience of hot water. So maybe there's a lot of homeowners that really don't care about, wasting water. Frankly, water is not very expensive in many parts of the country. But it provides the convenience of getting that hot water quickly. So it's also going to have the effect of saving water. But alas, not all hot water circulation systems are created the same. So there's a cost to operate these systems. And so I often use this analogy of an iceberg where the tip of the iceberg is the upfront costs, but then you have all of the operational costs. So if the upfront costs are the costs of the pump and the cost of putting in a return line, the operational costs are the costs that you typically don't realize unless you're really focusing on your utility bills. So if you look below the line, you have number one, you have the electricity to operate the pump. That's one cost. You have heat losses through your distribution pipes, and I'll get to more on that in a second. And then you have wear and tear, maintenance and repair from circulation flows that can create pinhole leaks, worn out heat exchangers for your tankless water heaters, et cetera, et cetera. Now, here's the big question for you all. If you were to guess what the biggest cost is of these three things, what do you venture would be? And I wish I had some way to take a poll right now, but I'll go ahead and give the big reveal. 90% of the cost to operate a hot water recirculation system is from the heat loss in the pipes. So when we talk about the energy consumption or the energy use of a hot water recirculation system, only about 10% of that energy is from the pump itself. Okay, so you can have the most efficient ECM motor pump, but if you're running that pump all the time, right, you're putting hot water into your pipes and you got water returning back to your water heater, and your water heater has to keep cycling on to make up for those distribution losses. So it's really coming from the water heater, and the runtime of the pump causes the water heater to operate more frequently. So the strategy is to control the recirculation pump. And there's been many different types of controls that we've seen over the years. The first one is no control whatsoever. Sadly, in many buildings, we see pumps just operating on a continuous 24/7 basis. We have timer controls that put the hot water recirculation on a schedule, trying to predict when you use your hot water. And so oftentimes the pump is still running for hours and hours out of the day. You have temperature controls, so like an aquastat that regulates the temperature of the loop. You have a combination of the two. You have variable speed drive pumps, which really doesn't turn the pump on and off. All it does is it varies the speed at which the water is being circulated through your pipes. VSDs have, kind of started off on the hydronic side and closed loop systems, and then they've sort of, meandered over into the domestic hot water side of things. So we're starting to see a lot more of those systems on the market. We see some new controls that supposedly learn your habits, and they operate the pump based on some type of an algorithm where it looks at your habits from the week before. Now, the problem with these types of controls, and I think we can all sort of, think about our own hot water use, on a day-to-day basis, is that oftentimes those hot water events are completely spontaneous and therefore unpredictable. Okay. So it's very hard, if not impossible, to know exactly when you're going to use hot water. And then last but not least, there's demand controlled, and only demand control accurately matches the operation of the pump to when hot water is being used. Let's see. I'm going to do this slide and I see some questions, so I'll get to that right after this. When do you not need to operate the pump? Well, if you don't need hot water. So if you're not at home, maybe you're at work, maybe you're on vacation, or maybe you're at home and you're sleeping or watching TV or doing something else other than using hot water, that pump shouldn't be running. And also, if there's already hot water in the line, so maybe someone just got out of the shower and your hot water line is now primed, and a well-insulated pipe is going to stay hot for a good 15 minutes, right? So the pump, no longer needs to run. And, once draw flow is moving the hot water through your pipes and it reaches the end, the pump does not need to be running. So you only need to turn on the pump just before you need it. And that's what demand recirculation controls does. It uses a sensor or a switch to turn the pump on that indicates the demand for hot water. And this can come in different forms. It could be a manual push button. It can be a motion sensor. flow sensor, wired, wireless activators. You can put them anywhere in the house. And then it uses a temperature sensor that tells the pump to turn off once hot water reaches the end of the plumbing line.
If you want me to read the question, we can go from
Yeah,
there. So not
yeah.
everybody can see that. So the questions ask if the biggest cost is the cost of the loss is through piping. What type of piping will be most efficient? Is it PEX? Is it CPVC? Is it copper? And is R3 insulation really enough for distribution lines?
That is a great question. I appreciate that. So I would say that the thermal conductivity in well, and I don't have the numbers in front of me, but I believe that copper is the biggest radiant. It's I mean, where I'm from in Minnesota, we use copper pipes to heat our to heat our air. We run it through heating coils made of copper and we blow a fan across it. So yeah, copper definitely transmits the most amount of heat losses. I would say probably followed by PEX, and then finally CPVC probably has the best um, insulative properties. But according to Energy Code now, any part of the hot water line that's at least three quarter inch needs to be insulated to the minimum R3 insulation value, and R3 is the minimum. But even if you do the minimum amount of pipe insulation on a hot water line, you're going to considerably slow down the cooling rate of that pipe. I mean, by a magnitude of 3 to 4 times. So having any pipe insulation is much better than no insulation at all. But obviously, if you can insulate your hot water lines better, that's better, right? But I think also cost has a big thing to do with it, as well as you can only put on a certain amount of thickness before you run out of space in the walls. But yeah, that's a very good question.
Yeah,
Um,
you answered that correctly. I mean, we know why PEX was put in. It's ease of use, it's lower costs. The good thing though is most of it is since it's so much cheaper, they run it through the attic, so it's covered by an additional attic blow if it's attic blow, or it's in an encapsulated attic with foam. Whereas copper, we normally did the shortest run possible, running it through walls, which are not. By the time it's installed through the cavity, it's closer to the outside than it is to the inside the way it normally is installed. So, and not usually insulated because they're hoping the insulation will take care of that. But yeah,
yeah.
I agree with you.
And I always forget how different they do the plumbing in Texas than in California. You typically you guys have the water heater in the attic, right? And that's where you run where you run your plumbing. Whereas
There's
California.
Yeah,
Mhm.
most of them are doing the garage, or they're doing
Oh, okay.
tankless in the garage, or they're even doing
Mhm.
tankless in the exterior wall. We have a few builders doing attic, but not a lot. A lot of custom builders will do tankless in the attic, but most national large production home builders are still doing them in the garage.
In the garage. Okay, got you. Yep, got you. Yeah, for many decades in California, they were running bare copper pipe in the concrete slab. And so, like, literally within a few minutes from using hot water, those pipes were stone cold again. So, there's so many homes that were built that way that, unfortunately, there's not much you can do without like completely raising the house and starting over. And so, that's why, plumbing is so important to get right the first time because, the plumbing is going to be the plumbing for the next 100 years. And so it's not just about how efficient your water heater is. It's really about how you strategically lay out the plumbing runs. Um, so anyway, here we see a configuration or a diagram of a recirculation loop where you have an on-demand pump on the return line, your temperature sensor, and then you have an activator at each fixture. That's each fixture in the house that either can be an occupancy sensor or a manual switch. And so again, as long as the loop is satisfied, if I walk into a bathroom and I walk in front of an occupancy sensor or push a button, the pump will not turn on because my temperature sensor says I'm satisfied. The pump does not need to run. So instead of pumps that are running, for let's say on a timer that could be running for 4, 8, or 12 hours per day, an on-demand system typically only sees about 10 minutes of runtime per day total. But you get all of the advantages um, of a fast hot water on demand. Now, there's also types of systems out there that you can install in an existing house that does not have a return line. And so the IECC has a code language that specifies if you're using your cold water line as the return, you have to limit the temperature of the water that's going back into the line. So you basically have to make sure that the pump turns off based on sensing no more than a 10-degree rise in temperature or about 105-degree temperature lockout. And the system must operate on demand. Now, I'll show you guys the actual language in IECC. So this is our version of it. It's called the undersink crossover, where we can go into a house without a return line and just cross connect the hot water line into the cold water line. The pump turns on based on sensing demand, and then the pump shuts off once the temperature sensor sees about a 6-degree rise in temperature. It sends a wireless signal back to the pump to shut off. And there's other different types of systems that are out there. Sometimes you have the pump that's located underneath the sink itself. But the key is that you need to have that pump turn off based on sensing either that rise in temperature or a temperature lockout.
I like that
So the
water heater
benefits,
picture, but sorry, Gabe.
yep.
There's like that water heater, but I'm sure there's a lot of inspectors that are cringing at that water heater picture with the just
Yeah,
taped together pipe. That's cringy.
yeah, very, very cringy. Definitely not up to like code standards. This is more of like a service plumber kind of doing his best effort. But certainly in new construction, things are held to a whole different standard, right?
Right.
So what are the main benefits to demand controlled recirculation? Well, number one, first and foremost, is you're limiting the runtime of the pump to only when it needs to, because you're looking at temperature and you're looking at demand. So again, you're only going to see about 10 to 15 minutes of runtime per day in total. So you're going to have more than a 90% reduction in distribution heat losses compared to systems that are just running that pump all the time. You're going to save somewhere between the magnitude of 3 to 10,000 gallons of water per year by not having to wait for that hot water. Um, and you get obviously the convenience of getting hot water fast. And I think that's what most homeowners really want and appreciate is I just don't want to have to turn on my shower and then go do something else for 5 minutes, right? I just want the hot water to come out right away. So it's the convenience factor. Um, On demand does meet IECC Energy Code requirements. And the electricity to run the pump typically is less than $5 a year to operate the system. So extremely energy efficient. And you're going to get a much longer useful life out of the system. I mean, if something is off 98% of the time it's not running, it would stand to reason that it's going to last much longer than other conventional systems. So here's some data that Gary Klein, who's the guru on hot water distribution, put together, and it shows that a demand controlled system versus one that runs 24/7, a system that runs 24/7 uses about 300% more therms of gas. And so this just kind of shows you the data, why and how energy is being lost, not just on the pump side, but on the water heater side. So what do the energy codes state? Well, let's first of all, just as sort of a point of information, is on-demand recirculation is a central component to a high-performing hot water distribution system, is laid out by the Zero Energy Ready Home program, which is a program put out by the U.S. Department of Energy. Lead for Homes and the EPA WaterSense now has provided guidelines for efficient hot water distribution. And so this language is pretty specific. In the past, we've seen language as it pertains to hot water recirculation oftentimes be pretty ambiguous, right, and open to interpretation. This is not. says that the circulating pump may not operate continuously on a timer or on water temperature, and gravity or thermosiphon circulation systems are prohibited, and that the pump needs to be demand activated by a momentary contact switch, motion sensor, flow switch, door switch, or voice command. And then after the pump starts, the control shall allow the pump to operate until the water temperature in the return line rises not more than about 10 degrees Fahrenheit or a maximum 105 degrees Fahrenheit. And another component of these energy codes say that the pump control shall limit the operation to no more than 5 minutes per activation. So in the event that you turn the pump on and it runs for 5 minutes and the return line is not sensing that temperature rise, then the pump is going to automatically turn off. And why do we do that? Because a very common issue with hot water recirculation systems is you get air trapped in the line. And then when that happens, the pump impeller is spinning, but it's not actually moving water. And then these pumps, they need to have water going through them. Otherwise, they will basically burn out. So this is a fail-safe to protect the pump from pump cavitation, this automatic 5 minute timed lockout. Okay, so and so now LEED also has a requirement that stipulates that the hot water source shall have no more than a certain amount of volume of water from the source to the point of use. So, for example, if you're running 3/4 inch PEX line from your water heater, then if you have 21 feet or more of plumbing, then you have to have a return line. And then that return line needs to be operated on an on-demand circ pump. So when you have a circulation loop that's primed with an on-demand pump, then they consider the primed loop as the source of hot water. So it's no longer the water heater is the point of the source. It's now the primed loop. And so that gives the builder a lot more flexibility as far as like their plumbing runs. And then WaterSense is again, WaterSense is very similar to LEED and the DOE's requirements as far as recirculation on demand. In California, we have what's called Title 24, and what their requirements are is that in new construction, if you're doing a recirc pump, it must be demand controlled with manual switches. So you can use the option of occupancy sensors, but there is a slight energy penalty. They calculate that, with an occupancy sensor, from time to time, you'll get a false signal for demand and the pump will, prime the loop. But the energy penalty is not anything too severe. But they do go into some pretty good definition of what it means. That the pump shall operate initially shortly before the hot water draw, and that manual control shall be located in the kitchen, bathroom, or any hot water fixture that's at least 20 feet from the water heater. And then same language as before about sensing the rise in temperature, so either a 10-degree rise or a 105-degree lockout, and then the 5-minute timed lockout for protecting the pump. Okay, IECC.
Before we
Yes.
jump into that, we have one question that came in the Q&A back to what you said earlier about the pump running dry and having cavitation. Is there a procedure or how do you recover if the pump shuts off due to air in the lines?
That's a great question. And I have a slide that's coming up that's going to show you exactly how a proper return line needs to be configured in order to bleed the air out of the line. So that's a great question. I'm going to get to that in just a few slides.
Thanks.
So IECC, they say that controls for circulating hot water systems shall start the pump based on the identification of a demand for hot water within the occupancy, and that the control shall automatically turn off the pump when the water in the circulation loop is at the desired temperature and there's no demand for hot water. And so immediately after that, they have another section that even further clarifies what demand circulation means, which it shall start the pump upon receiving a signal from the action of a user of a fixture or appliance, sensing the presence of a user of a fixture, or sensing the flow of hot or tempered water. And then, so that's turning the pump on. Part one is turning the pump on, and then part two is turning the pump off based on sensing the temperature. And like other energy codes too, we've seen IECC get more explicit over the iterations, right? In 2009, it was very vague. It was very, that you should have a pump that turns off automatically or manually when the hot water system is not in use. And then over the years, it's become more defined about what on demand means. So there's four main components to a demand recirculation system. You have the pump, you have the controller, which can be either integrated into the pump or it could be separate from the pump. You have an activator, which can be wired or wireless, and then you have a temperature sensor. It is recommended for residential that you size the pump. So, a lot of tankless water heaters have a built-in recirculation pump, and it's a very small recirculation pump. And if you're operating that pump on demand, and the pump is, let's say you have that tankless in a very large, 4,000 square foot house, it might time out. It might take longer than 5 minutes to prime that loop. So, we always recommend that you size the pump based on the size of the house and the length the length of the plumbing run, so that when the pump is activated, you get the hot water in the quickest manner. Because the faster that you're running the water through your line, the faster that the pump is going to shut off. So we hear oftentimes questions about like, well, Uponor says that you shouldn't run or you're not allowed to circulate at more than a few GPM in PEX pipe. Well, they assume a 24/7 recirculation, right? So on demand is a different category altogether because we're only running it just for those brief intervals. So how do you configure the loop is just as important as how you operate the pump. So there's the guidelines in WaterSense are saying that okay, number one, you want to minimize the piping. And right now there was actually just a few weeks ago, the New York Times had a cover story that of all things had to do with this research right now on reducing pipe size in plumbing and creating new codes for minimizing pipe sizes, which I thought was an interesting story for the Times to run. But the heat losses in a distribution system is largely a function of the surface area of the pipe. So if you can reduce the piping, you're going to minimize the heat losses. So we recommend the loop be no more than 3/4 inch, and then you keep the branches to a 1/2 inch. And if you can minimize the distance of the branches from within about 15 feet from the main circ loop, and you're insulating all of the trunk line, make sure that you use sweeping radius elbows versus 90, hard 90 elbows, because every 90-degree elbow in a plumbing system is the equivalent of adding 3 extra feet of piping from a head loss standpoint. So if you take all of these things into consideration in your plumbing design, when the loop is primed, you'll never waste more than about 2 cups of water waiting for hot water at any fixture. So that's the goal, is if we can achieve this, then you're going to have a high performing hot water distribution system. Now, to go back to the question about purging air out of the line, which is a very common thing, air gets in our plumbing pretty easily, either through the city, or if maybe you're doing some, maybe you've replaced a water heater or replaced a plumbing fixture that required you to shut off the water to the building. In either case, it's very easy for air to get caught in the line. Now, when hot water comes into your supply line, it will naturally come out of your fixtures, out of your shower or out of your faucet, and you actually can see the air getting purged out. It just basically coughs, air. But when that air finds its way into the return line, because you have a check valve on the return line, you can't, there's no backflow, right? So that air just gets stuck in there. And then the pump, when the pump is running, it's not actually able to move water. So what you have to do is you have to install what we call a bleeder valve. And a bleeder valve is just like a hose bib that you put downstream of the pump. And if you ever run into a situation where the pump is running, but the return line is not getting hot, and the pump itself is like, burning hot to the touch, that's like the surest sign that you have airlock. And so all you have to do is just open up that hose bib, that bleeder valve, just attach a hose to it and run the hose outside into the front yard or whatever, and you'll see that water, you'll see that air getting purged out of your return line. So this is becoming part of code now too, to add these bleeder valves on return lines, and it's very important. Just as important to have that as it is to have a check valve on the return line. So here is a picture of a hot water recirculation system where you have the tankless water heaters, you have your hot water supply going out to the house, and then your hot water return line coming back, which is completing the loop. Where it says T1 here, this is where the temperature sensor is located. And then you can see where that bleeder valve is located downstream of the pump. You want to make sure that the bleeder valve is downstream of the pump, because if it's upstream of the pump, then potentially you'll never be able to, fully purge air out of where the pump is. And then downstream of this bleeder valve, you want to make sure that you either have an isolation valve or a check valve or something that prevents backflow, because if you open up this hose bib and you don't have any type of check valve or isolation valve here, then what's going to happen is just the cold water from the city is just going to come in and just short circuit, and you're never actually going to bleed out the return line. So that's why things have to be done in the right order. Another picture of some return lines with pumps, controls, where you have a bigger home that actually split the loop into zones. So if it's possible, you want to minimize the circ loop if the loop is too big, then you may want to consider dividing it into zones. So what type of methods for activation? We have hardwired activation. These are momentary contact, normally open switches. So think of like a doorbell. A lot of builders are putting a little push button activator near the light switch or near the fixture itself. And so that commands the pump to turn on. They have, there's lighted switches that turn on, that they illuminate when hot water is ready. So if there's hot water in the line, this indicator will tell the homeowner, okay, hot water is ready. All I got to do is turn on the faucet. And then when the lines cool down, the light will turn off. And that is prompts the user that they need to prime their loop to get hot water. So manual activation will ensure that the circulation pump only runs when there's hot water demand versus like an occupancy sensor. But occupancy sensors are a good option as well to fully automate the system. So if you don't even ever want to think about it, you can just put these occupancy sensors near the point of use or near the bathrooms. And then that will ensure that the pump never turns on if nobody's like up and about the house.
Quick question on those sensors, Gabe.
Yes.
Can those work double duty? In other words, if it's a sensor already for an occupant sensor for a light, can you wire it to that to kind of do the same thing? I'm just trying to.
Yeah, that's a great question, and I think I've been getting this question more and more frequently. I believe that the way that the switch operates is that it's kind of like in the reverse. So I believe that the light switch occupancy sensor is like normally closed, where this one is normally open and it's just momentary contact. I think there's a way to do it, but the occupancy sensors that are being used for light switches now, I don't think that they would work. there would have to be some sort of alteration to those switches, but I predict that, there'll come a time when it will basically do both the lighting and the recirc system. So yeah, but that's a good question. When you're hardwiring, typically you want to do it in a home run fashion. So the fixture has to run a home run all the way back to where the water heater is, versus connecting in the walls, because you want to be able to test the continuity of each individual switch. So let's say if my water heater's in the garage and I have 5 motion detectors, I want to see 5 wires coming out of the wall so I can test each one individually. There's wireless activation, so you can operate the system from, and this is great for retrofit because you don't have to run low voltage wiring. So typically these have a range of about 1,000 feet in open air, so you can, literally keep one of these buttons on your nightstand. So when you wake up in the morning, hit your alarm clock, hit the little wireless button, and the time it takes you to walk to your bathroom, the hot water's already there and the pump's already turned itself off. Verifying if a recirculation system has a demand control. Okay, so let's say you're an inspector and you want to know, well, is this pump an on-demand system? So the first thing you want to know is there a temperature sensor connected to the return line? And if so, if my return line is hot, then that pump should be off. If anytime that the return line is hot, that pump should not be running. And is it a known manufacturer of on-demand systems? So right now, I would say that like the most prevalent on-demand systems are, the Takeo Genie, ACT Demand. Of course, we have our AutoHot system. Grundfos has a on-demand system that meets Energy Code. And there's some other ones that are on the market too. And then you want to verify that there's some type of an activation switch at the point of use, either a push button activator or a motion sensor, or it could be a flow switch that's built into the plumbing itself. We've seen systems out there that use a little flow sensor that anytime someone turns on hot water, that flow is the demand sensor that turns the pump on. So other than residential, there's good application for these types of on-demand systems, and what I would call light commercial. So smaller commercial buildings like office buildings or restaurants, or maybe a gym that has a water heater that serves just maybe 10 or fewer fixtures in the building, where you can hook up occupancy sensors. So let's take for example a restaurant. They have a very predictable schedule, right? A restaurant may open at 6 a.m. and then close at 10 p.m. If you've got an occupancy sensor in the back of the house, and maybe one in each of the lavatories, then that pump is going to stay off. Anytime that there's nobody in that building, that pump is going to stay off, and then it's only going to stay on as long as it takes for the hot water to get through the loop. So, just remember that if you have the occupancy sensors and people keep walking in front of the occupancy sensor, it doesn't mean that the pump keeps turning on, because as long as hot water is in the line, then the pump will stay off. So here's an example of a commercial application where we saw there was a circulation pump that was circulating the hot water from the main boiler room to a commercial laundry room, and it just ran 24/7. So this was not the circulation pump that was serving all of the rooms. It was just for this one area. And so, we thought, this is a very easy pump to control. So we just installed the control that has a little temperature sensor on the return line. And then we hooked up if you can see this middle picture here, there's a little wireless motion sensor, so that anytime somebody was in the room actually doing laundry, that's then and only then was the pump turning on. And then it was only running for, a minute or two until the return line got satisfied, and then it shut off. So instead of running 24/7, now it's only seeing about 10 minutes of runtime per day. So this is just an example of a commercial, light commercial application that you could consider. And then we also see other applications where a lot of commercial kitchens, in order to meet health code, they have to get hot water at certain fixtures. They got to get 120-degree water within a certain period of time. And many commercial kitchens aren't able to achieve that because of just how the design of the system um, just did not permit for hot water to get there as quickly. So you can always install one of these under sink retrofit type of pumps, of which there's many there on the market. And then that way you can prime that dead leg branch line. Let's say you have a 40-foot branch line that's coming off the circ loop, half inch, and it's still taking a minute or two to get the hot water there. This way you can install that secondary pump and get hot water at the end of any problematic branch line. Last but not least, I want to address heat pump water heaters. And I know that I don't know how prevalent heat pump water heaters are yet in the Texas market, but I can tell you they've hit the California market like a tsunami. It literally was like a switch being flipped, where builders went from installing. Well, first of all, when I moved to California, it was all tank water heaters in new construction. And then the energy code went into effect. It's got to be tankless, and then it's got to be condensing tankless. And now everything installed in California now has to be electric heat pump water heaters. So the pendulum has swung right back to tank water heaters. But it's important to note that these do not operate like like a gas-fired water heater. The recovery time is much longer. It's just a completely different beast. And I'm sure that at some point these will start to hit the Texas market pretty big, just because Texas has got a really good climate for the very favorable climate for these types of systems. Because if you have even the most efficient tankless water heater, you might be able to get 95, 96% thermal efficiency, whereas with a heat pump water heater, you can achieve up to 400% thermal efficiency. So the efficiency is off the charts. For every 1 unit of energy, you're going to get 3 to 4 units of hot water output. It's really great in areas where they work. There's no combustion, there's no carbon emissions, and it's a central technology to decarbonization mandates. But the problem with heat pumps is that they generally do not like recirculation pumps. And so a lot of the manufacturers are saying, well, if you're combining a recirculation system with a heat pump water heater, you need to either have it on a electric resistance mode, which basically is turning on these little heating elements, and then you lose all of your efficiency from the heat pump, or you have to have an on-demand control. So recirculating hot water excessively in a heat pump is going to diminish the heating capacity as well as the coefficient of performance.
Yeah, Gabe, on those, just real quick, heat pump water heaters are gaining ground, but as I said, a lot of builders still put them in the garage. They have pedestals that they're sitting on. These heat pump water heaters are taller, but
Yep.
once everyone starts to realize that it's a free air conditioner for the
Oh yeah.
garage, and then you've got the argument of you really need the water heater taken out of the garage and have it more of a centrally located, but then that's going to take away the air conditioning that they're getting for their garage. So yeah, I like to
Yep.
see when the efficiency is off the chart and there's benefits to it, just even not just the efficiency of heating the water, but we're still probably 3 to 4 or 5 years away from being commonplace.
Yeah. Yeah. No, and I get it. And that's most of the country as well. We're just at the very beginning of this kind of like transition from gas to electric. Gas is still very cheap, right? So it's going to require a lot of uh, yeah, it's going to take some time for it to become sort of mainstream. But I think a lot of builders are also kind of taking the initiative to do more of their projects using heat pump water heaters. But the thing about heat pump water heaters is that yeah, if the pump is running excessively, you lose all the efficiency and you're going to lose heating capacity. So all the major manufacturers now, from A.O. Smith to Rheem to Bradford, they're all saying that you need to use some type of an on-demand system that meets the energy code requirements. And that way you can preserve your efficiency. It'll stay in heat pump mode. It won't be kicking on these heating elements, or you won't be running out of hot water. So that's the benefit to marrying an on-demand system with a heat pump water heater. But for now, it sounds like tankless is still kind of like dominating the Texas market, and I'm sure many of those tankless heaters have the integrated recirculation pump. And many of those tankless water heaters, by the way, have the capability to operate on demand because they have to meet that requirement in California for Title 24, and they're pretty strict here about enforcement of on-demand recirculation. So if you look at any one of these heaters, Rinnai, Norris, Rheem, you name the tankless, the ones that have the built-in recirc pump, they do have the ability to operate it on demand. With
Yeah,
that, I'll open it up to any other questions.
yeah, we had
Let's
a
see.
question that just came in the Q&A. Says, can or should the MEP designer account for the reduced load needed for HVAC when replacing it with the heat pump water heating? That's a good question, but that's a
Um,
rabbit hole.
I would say probably not, because, like as we were just like Randy was just saying, a lot of times a heat pump water heater is put in a garage because in order for the way that these heat pumps work is they take the air from the surrounding environment and they put it, they use the refrigeration process to put it into the water. So that's why they call it air to water heat pumps. And so you need a significant amount of cubic feet for that, basically for that heat pump to breathe. And so you can't put a heat pump in like a broom closet, for example, right? Unless that door is louvered. And so the best place to put a heat pump water heater is in either a large attic space or in a garage where it can absorb the surrounding air, right? And so if you're putting it in the garage, then that's unconditioned space, right? You're going to be the cold air that it's discharging is just going to be like cooling in unconditioned space anyway. So I don't think that it would affect unless you're deliberately venting the cold air back into the building envelope. I don't think you need to. I don't think that you need to consider that at all as far as like HVAC design.
I think that would be again going down that rabbit hole. It would be so let's say I have a utility closet or utility room that's probably 15 by 9 or something, and it's a high volume ceiling, and you put that in the corner of the utility room. The the rabbit hole is going to be is now the homeowner's complaining that that room's always cold. And so,
Right.
because it's venting off into that, it's just never a good idea to design it that way. I don't know that you would build a closet big enough just to say that's just for the water heater because that's where I'm going to put it. I think that's almost where it would just be out of the home's envelope. It'd be in the attic, centrally located in the home, or it would be in the garage, and you wouldn't be able to account for that. I mean, it's a great question, but it's a rabbit hole you can go down of a what if this and what if that.
Yeah.
So
I'm
another
definitely
question
not.
is,
Yeah.
go ahead.
Mhm. No, I was just going to say I'm definitely not the authority on that. So
Right. So another question, Juliana is typing an answer, but it says tankless is an electric version comparable with a gas tankless, or would you know for that?
again, comparable in what way? Like efficiency?
Yeah, probably. And the cost,
The
like
answer is
annual costs.
Oh yeah, so the answer is that electric resistance is higher efficiency than any gas because with gas you're going to have combustion losses. With electric, you don't have any of those combustion losses. You do have standby losses. Well, actually, with a tankless electric, you don't have any standby losses, and you don't have any combustion losses. So it is going to be more efficient. However, the cost is going to be much, much higher on an electric on a per energy unit basis. Water heating using electric resistance is much more expensive than gas.
Yeah, I
Um,
think that's just going to be one of those things where if you don't have gas to use, then if you really want tankless, there are efficient ones out there to use, but I don't. Yeah, I don't think that
yeah, if gas
you
is
wouldn't
not an option,
supersede a decision of gas over electric just because you prefer all electric. I don't think that would be the case.
yeah. If gas is not an option and electric is the only way to go, my choice would be to go to heat pump, just given the efficiency that you get from an electric heat pump water heater.
Yeah.
Um, but yeah,
Yep.
good
And then one
questions.
other question in here says, can are you going to share the presentation?
Oh, absolutely. Yeah.
Okay.
How do you want me do you want me to send it to you, Randy, or how
Yeah,
should I?
if you want to send it
Or
to me, and then
here's
I'll let Kathy send it out with the survey email.
okay.
Yeah,
Yep,
we can do
absolutely.
that. And then also one other in the chat, I kind of answered the question, but Casey is one of he's a real estate inspector that's going out there looking at energy stuff. He's
Mhm.
basically saying, which I agree with, that what you just talked about in the recirculation pump. I mean, other people were asking, are we seeing this in production homes? I think that's going to be a yes down the road in the near future. Because home builders are always looking for reducing warranty callbacks and issues with the home. And he's basically saying that doing his inspections, it is probably the number one or one of the number one questions he gets all the time is how can I get a shorter time between getting hot water? Because if the
Yeah,
complaint is it's in the garage, the longest distance to the master, things like that that's not thought about. And I think
yeah,
eventually homeowners or builders, home builders are going to see this as reducing warranty callbacks and issues. Before it was always we just didn't really have a good technology. The costs are
hmm
too high. Now I think that's going to be a moot point in the near future.
yeah. That's a really good point. I remember, hot water circulation wasn't all that prevalent here in California for a while. And then, but in my first slide, when I was talking about like new home construction taking much longer to get hot water, and so as real estate, started to, real estate values started to grow, people were, moving into their $1 million house, and they're like, why am I waiting 5 minutes for hot water in the master bathroom? So a lot of these production builders kind of like got wise to, well, if we want to, we might as well just put in that return line, spend the extra $2,000 or whatever it's going to cost, put in the return line in order, so that we minimize those complaints. And then I don't know, and now we're starting to see more jurisdictions actually implement like more water conservation, like in the plumbing. Like for example, the city of LA now says that they've adopted like the lead language of you can only have X amount of volume of water in the pipes before it's required to have a dedicated return line and a recirculation loop. Um, so yeah, I think a lot of production builders are starting to like move more towards recirculation systems. And then it's just about, okay, well, which one works the best and which one, is gonna, you know, provide the most efficiency. And um, but yeah, it's still, I've been living in the recirc world now for so long. That's all I kind of like live and eat. But I forget that most people don't even know what a hot water recirculation system is, right? All they know is, and they've just come to expect, okay, I've got to wait for hot water. I'm going to turn on my tub spout and then I'm going to you know, go get the paper or go do something else. And by the time get back, then the water will be hot, right? Um, so it's still kind of like, kind of at the forefront, I would say.
Yeah, but in a reason I like having you guys on to do this is, because some people look at this and go, what does that really have to do with energy? I understand it's a code thing, but It's in the IECC. So if I'm a plans examiner slash residential code inspector, either that or I'm a building official, if you're looking at it from the IECC standpoint and suddenly you walk into an 8,000 square foot custom home, they've got a recirc system. Guess what? You got to go get the book or open up the digital online because you're going to have to verify all this code requirements for when one is installed. Is it installed correctly? And a
Yes.
lot of times, I did inspections for 10 years. Most of my guys would look at that and wouldn't give it a second glance because they don't really know what it is when they don't see it for the most part. And suddenly it's there. But now all of a sudden you're scrambling trying to find out what is the code requirements that I'm looking for.
Yeah, and it also kind of goes back to what I was saying about how in the past the energy codes were very vague and ambiguous. And so it was basically you could put any kind of control on the pump and that basically was, that kind of checked the box.
Yep.
But now they've gotten to be pretty descriptive about what it all means and and why it's important. So yeah, there's not a whole lot of actors that are pushing this technology. We're one of them, but there's other companies that are out there that have something similar, and I think it's a matter of like just taking time. I remember when again, to use the example in California, the energy codes 2013 was when it went into effect, and we didn't start seeing it become more mainstream until like 5 years later.
Yeah.
Anytime there's a change to the energy code, it always just takes time to figure it out.
Yeah, and then one other question here basically says, what's better R3? What's better than R3 for insulation without being an overkill? Manufacturer's probably going to make a 3 and then a 5 and then something like that. So I think just stepping up to the 5 would probably be better,
Oh yeah, I
um,
mean, if you
without being an
anything
overkill and
extra.
cost burden.
Yeah, I mean that's the balance, right? Is what's the cost burden of going from R3 to R5? If it's a negligible increase in cost, or maybe it's just a little bit thicker, wall, insulation wall, then I'd say do it because it's incredible how much insulation keeps your hot water line hot. Where if you prime the loop, the pump might only need to run, a few minutes a day total. Um, so yeah, but for builders, it's all about cost, right?
Yep. Cool. Well, I appreciate it very much. And then one thing there was someone that posted something in the question Q&A kind of made me laugh because I always used to say this when I did it was it's not a hot water heater, it's a water heater because you don't reheat hot water. It does take you a long time to change the language, and I had a
Yeah,
problem with that as well. But
hot water
guys,
heater. Yeah.
I appreciate very much all of this. We will share the slide deck with you via the survey email that Kathy Lawrence will send out, and then we'll continue to have these guys in the future or on in the future, so you guys can continue touching base. Because I do believe, just like Gabe and I talked about, this is going to be something that's more commonplace, even with production builders installing these things to set themselves apart from other production builders and trying to be more energy efficient. So can't thank you guys enough for that. I appreciate it. Be sure and join us next. It's going to be next year, January 21st. We're going to dive back into HVAC ductwork field inspections. It won't be a live or a recorded session because that was kind of shaky. It's going to be a lot of field pictures about what to look for. And basically, we're going to dig into more of the what effects does this have on poor installation having effect on airflow. It has a lot to do with airflow, and that's why it's so important when we're doing energy inspections is to look at the ductwork and how well it's installed. Again, here's my contact information. Be sure and share that with anyone that might need us for anything or anything I can do to help with answering energy questions, energy code questions from plan review to field inspections as well. And then being able to reach out to guys like Gabe and Juliana with those two companies that can help us work through these things that are not commonplace yet, but we'll get there. And we're going to have a lot of questions on what it looks like in the field. So thank you guys again. I appreciate it very much. And everyone have a safe and great holiday. And we'll talk to y'all next year.